calculate pH of solution. I show this. So formic acid. Hydroxide. Okay. When you multiply this guy, that will be 4.8 millimole. 4.8 millimole. And you take hydroxide, you multiply 7.5 millimole. We have more of strong stuff than big one. This is before titration. After titration, you're gonna have nothing left. Everything be used up. That will convert to conjugate 4.8 millimole. Here, if you lose 4.8, that will be 2.7 millimole. So after. So from this situation, we have to identify what situation we have. Do we have buffer? Do we have a buffer here? No. We have strong base and conjugate base. So this is not a buffer system, and it will just ignore weak base. It's only strong base. So, but that's more millimole actually, 2.7 millimole inside of what volume? Well, 40 milliliter plus 75, 115 milliliter. So that make it more relative as some number. So your QH is relatively low of that number, and pH will be 14 minus this number. If you did it this way, you should get right answer. This. Okay. We have ammonia with strong acid. Okay. At the 50 milliliter of HCl. Alright. So we have ammonia and adding strong acid. That will make it ammonium. Then before titration we have ammonia 100.5. So 50 millimole. 50 millimole. 0.5, 50. So that will be 25 millimole. Do you have anything else? We don't have ammonium. Right. So after titration, nothing left here, but that will make 25 millimole of ammonium, and half will be gone, 25. So we have a buffer. But we have a buffer, pH. They are asking what? Concentration, hydrogen. Okay. So pH is equal to pKa. So we know that amount is equal. So then will go away. So pH is just pKa. That means H plus concentration will be equal as Ka. And Ka is given, not given. Therefore, 10 to the 14 kb. So that will be your hydrogen solution.
I'm sorry, can you finish solving that one? I'm so lost.
Oh, here?
Yeah.
Okay. 10 to the 14 divided by kb. kb is 1.8. 10 to the 5 difference. So that will be what? I think maybe 5.55 10 to the minus 10th. That will be equal to concentration. number may be right, but you have to check.
Okay.
I think identification before, so the number may be right. How many milliliter of HCl will be required to reach equivalence point? So we need to put equal amount of, so HCl titrate ammonia. Now we know the constant is equal, therefore you just put same value, which means simply 100 milliliter. Right? Because constant is equal. Calculate pH when this acid added to solution of this. Okay. So, let's see. So I have HCl. If I multiply it, 10 millimole, 10 millimole, 10 millimole, 10 millimole is added to this guy, and we have 0.050. So again, 10. 10 millimole. And then what else? That's it. We don't have anything else. That is before titration. So after, if we have the equal amount, that turn it to 0, that will make it 10 millimole of conjugate action. So we have just sort situation. Therefore, starting from this guy, we do ice table. Or, yeah, ice table. So, I'm gonna call this one as pH plus, because that is from base, it's conjugate action. So pH plus, we are hydrolyzing the water as P and H plus. And then we initially we have 10 millimole. 10 millimole. To find the concentration divided by volume. Total volume is 15 milliliter plus 50, which means 100 milliliter. 100 milliliter. Wait. This one is 0.1. 0.1. So relative to 60. Okay. So at equilibrium, I'll have 0.10 minus x. This guy is x. That guy is also x. So if you do ice table, x square over 0.10 negative x is it Ka or Kb? It's Ka or Ka, right? Because
Because you have H plus.
reactant is acid. But the Ka value is not given. Kb value is given. So you can do in here 10 to the negative 4 or 14 divided by Kb. And then this side you can just simplify 0.10 as a approximation. And this side you just put this guy right here and solve for x. So my x will be inside of square root 0.10 times that guy. For my x is H plus. We know that is hydrogen ion. What are they asking? pH. So just take this value, negative rho, find out pH. Okay. calculate the equilibrium concentration of ammonium ion in a solution that is ammonium that, okay? So ammonium, so we want to find the concentration of ammonium. So we want to find this guy. And ammonia concentration is 0.060. And then this guy is 0.027 molar, but that one mole of this guy release 2 hydroxides, so it will be twice of that, 0.054 concentration. So that's the initial condition, and we need to find the equivalent condition of this value. So at equilibrium, let's call this one as x. Okay, we want to find out x. So x amount will dissociate. That will make it x amount of product, and this product will be 0.54 plus x. So my k value is product over reactant, and my reactant is base, so this is Kb, and then Kb is just given right here, right there. Now on this side, you're going to assume x will be small. So you can find out x as 1.8 10 to the 5th times 0.060, because you have to flip on the outside, 0.054. And x is my, what am I calling it? Okay, NH4 plus, NH4 plus. So that is my NH ammonium ion, and that's what they are asking. Now notice that I didn't have any time constraint, so I just feel comfortable solving all of this. But you have to do it within the time limit, right? So you need to be comfortable with any of this situation, so you don't have any problem that way. Any question?
Yeah, but I can't put it to words. I don't know that if you were to give us a second chance on this quiz that I could still get those problems right even after you just explained it.
Oh, okay.
Is anyone else feeling in the same boat, or is it just
It's
me?
like it's easy once you know what to do, but it's like when to do things.
Yeah.
That's what I explained. Like JJ,
Yeah.
I was gonna I printed off the practice exam, and so I was just gonna go in Learning Commons and do it, and like when I get stuck, figure out when to use things, because like
Right.
I don't know when to use things.
Yeah, so in this situation, because there are multiple different scenarios, when you look at the problem, the first thing is before you do any calculation, you have to identify what approach should I choose to have this problem. So when you look at this, for example, I have weak acid with a strong base, but it depends on the number. So after this, we can identify, oh, okay, that's just strong stuff, right? We have weak base and strong base. So strong base will prevail. So problem is, that kind of problem is, after stoichiometry, you just find out, oh, that is strong stuff.
So if it's not a buffer, you just take the strong number for it?
Yes.
Okay.
So you have two kind, but it's not conjugate pair.
Mm-hmm.
Then even on weak stuff, just only consider strong stuff.
Okay.
Now here, after you do stoichiometry first, remain species is conjugate pair. So you identify, oh, this is a buffer problem. If it's a buffer, use Henderson-Hasselbalch equation. For first one, because it's strong stuff, you just use pH is negative low version of this formula. Okay? It could be pOH, but anyway, if it's strong, use this formula. If you identify the buffer, Henderson-Hasselbalch equation. What is the next one here? This one was salt problem. Why? After stoichiometry, only thing remaining is salt. This is a salt problem. If it's a salt problem, and then that is weak stuff, you set up ice table. Okay? If it's a salt, you're gonna use ice table.
So on B25, if you're using the Henderson-Hasselbalch, and the middle equation, pH equals pKa, I understand how you get to that point. But then how did you jump from there to the H plus concentration equals Ka?
Okay, because this will cancel after this. So this is will be pH equal to pKa, and then I'm just dropping P at the same time.
Because you're at the equilibrium, or because you're at the equivalence point, those are equal? Okay.
Because at the equals, wait, not equals point.
Oh,
It's the midpoint.
the midpoint.
Just
Okay.
because 0.1 over 0.1 is 1 and log of 1 is 0.
Yeah. At the midpoint, conjugate pair will have equal concentration. At equals point, we have a differentiation. This is 1 equals point. At equals point, we have a salt. Okay? At equals point, we have a salt. And then before titration or after titration, you're gonna have a
When it's pH
strong
equals
stuff.
pKa,
Mhm.
you still have to find out what pKa is. So how are you going to do that? You have to find the Ka. So you do the equation.
Oh, you
with
take off the
Kb.
P's.
Yup.
Okay, I got
And
you.
then you're getting
Thank
the Ka.
you.
That gives, yeah.
Perfect, thank you.
So at initial point and beyond the equivalence point, we are dealing with strong stuff. Okay? At equivalence point, we are dealing with salt. Anything in between, we are dealing with a buffer. Okay? So, yeah. So that was salt, and the conjugate base, you're gonna use. So when I say salt, this is ion. Salt will dissociate, producing ion. So that will be a ice-table problem. So the last one, what did I do? Okay. So we have both kind, but the thing is, yeah, this is a. What is it? Different concentration. You have ammonia and this. Oh, this is common ion problem. This is a common ion problem. So without this common ion, it could have been a weak, just weak acid. No, yeah, weak base problem, right? So it could have been ice table, but because you have, so we can still consider this is ice table, but with common ion. Okay? It's ice table problem, but with common ion. Okay?
And which one's the common ion? I'm sorry.
Wait a minute. No. NH3. No, it's not common ion. Let me see. Here, okay. And then you have inside. Okay. No, it's it's not a common ion, but what's that? What's that called this guy? It's not common ion, just approach is similar, but it's istable. What should I call? What should I call? No, just istable, but it has something else, something extra. So it's just similar to common ion, but it's not common ion itself. When we have common ion, we have dissociation, and the common ion will change the istable setup. So it changes istable setup, but it's not common ion. Because you said it. Yeah, it's not common ion. Okay. Any question? Wow. So that's what you because this is the problem you're gonna see it. So yeah, reviewing this problem was important. Let's move on to. Is it okay if I raise it?
Told me I went and started. I'm like, I don't know when to do any of this. Like it all looks the same.
Right.
By the way,
I think your idea is a good
have
one
you
though.
checked in the
It's a good
announcement?
place to start.
Yeah.
I have
So
a lot of those.
just in case somebody, anyone who didn't check the announcement, do you know that the exam is total 500 points? Okay, exam. From Unit 1 to Unit 4, one of them will drop. That give you 300, and the final one and final two, 200. So together, 500. Now this in-class quiz, what we are doing is total 60 points worth, okay, quiz. So this will be very helpful to boost your grade, but it will still, this one will determine your grade, right? This is about 1/8. So it will be helpful, but this is the thing. You haven't done the in-class quiz so far, like how many, like every quiz hour. So look at your quiz, and then in the detail you may see the percent point for that, and then the average. So if the average is less than 64%, that means that's the score you're gonna get from the exam, which means you do not passing, you don't pass this class. Okay, so check your average percentage from the quiz. If you see less than this, you have to do something. You should change something, because if you keep doing this way, you will not pass. But the thing is, the good news is that when we do not include the bonus point, quiz not only is indicator of how you're gonna fare in the exam, but also it gives you bonus point. Okay? So there's some cushion here, but do not rely too much on this bonus point, because that's only 1/8. Okay? So please make sure find out what your average score from the quiz, and then think about how much you have to put more effort, okay?
This is what I put. Like, I was just gonna go through it with him, but it has like all the questions, types of questions we do. And he like isn't allowed.
So in our titration that we try to find the end point. No, actually equivalence point. Equivalence point is where theoretically amount of acid equal to amount of base. That's what equivalence point. But human eye cannot identify equivalence point. We use indicator, and then based on change of color of indicator, we find the end point. So we try to use right indicator that will fall exactly very close to this number. Okay? But sometimes there might be different. But that difference between those 2 points is what we call tight fusion error. Okay? So titration works just like that. Let's say we have weak acid titrated with a strong base. If we have enough of the base, then neutralize all of acid. That's when extra base will titrate indicator. Indicator is actually weak acid itself. Okay? So this guy neutralize all those acid, and then the moment it starts neutralizing indicator. So this is neutralization of original acid, and then additional hydroxide is neutralized indicator, making conjugate base of indicator. This guy normally has color. For phenolphthalein, weak acid of indicator colorless, conjugate base of indicator have pink color. So this neutralization will make conjugate base of indicator. That's the color we can see. The thing is, human eye can identify when this conjugate base is like about 10 times of concentration of indicator, of weak acid form of indicator. Okay. Because of that, we normally see that pH, when we see the color change, that is actually plus or minus 1 of pKa value. Okay? So you use indicator, and then you think, oh, there's a change of color. So you are on the aqueous point, but there might be error, plus minus 1, because that's the limit of human eye. Okay? Because of that, most indicator has about plus minus 1 range, which means pKa value is in the middle and plus 1 or negative 1. That's the range we can use for most typical indicator. We are not going to do any calculation about indicator that is a lot more complicated than regular acid. Okay? Because you are using regular acid plus indicator as acid. It's more complicated. So we are not going to do any math portion. Just understand the plus minus range of indicator, that's enough. What indicator should we use if we want to identify that guy? So we have weak acid here and strong base. Okay? What indicator should we use? P K A of indicator should be equal to pH at equivalence point. So for this guy, we have a
Where did you get the .05?
That's very good question. When you do titrate, and then you have same concentration of both, right? So you're gonna have to put equal amount to get to an equivalence point. Do you agree? Because you have equal concentration of acid and base. If you're gonna titrate, you have to put equal amount. So we'll see that even though we don't see any volume will double, which means concentration will be half of it. You have to be careful. Are you with me? Because when you have acid base with the same concentration, when you neutralize it, you're gonna have to use same volume of each. So then make it twice of volume. That will make it half of concentration.
So we should know that's at the equivalent point.
Yes, because
Give equal.
pKa indicator should be equal to pH at equals to point.
Okay.
So what number do you get? Do you get any number? So I didn't get it. Let's see. hydroxide concentration inside the square root, is 5 times 14 divided by 1.8 5. So that will be x. It's not 5.27. Negative, what is that? 6. Okay. You put that number, negative log of that number will be 5.27. 5.28. So 14 minus that number is 8.72. 8.72. So now you know that pH is this number. Choose indicator whose pK value is similar to that guy. That would be phenolphthalein. So you have to choose phenolphthalein for your titration.
Can you explain one more time how you got 0.05?
Yes. Okay. We have no idea about the volume from the question, right? But the thing is, we are titrating acid with the base, and then what we know is they are in same concentration. So if you have same concentration of both acid and base, when you titrate, you need equal amount, which means same volume. You need the same volume of both. So if I mix 0.1 molar concentration of something with another, because volume double, concentration will become half of it.
So it doesn't matter that it's a weak acid and a strong base, it would be the same regardless.
If that was strong guy, you wouldn't worry about isotable at all.
Mm-hmm.
So that was true. Even for the strong guy, you may have if that was strong guy, you do not worry about this conjugate base. For example, HCl is strong acid, and then if you titrate the strong base, A minus will be just chloride. Chloride would not hydrolyze water, so pH will be just 7.
Right.
So
Okay.
let's say we use strong acid, titrate the strong base, pH will be 7. We don't have to do any of this calculation. So you can just choose indicator that whose pKa value is similar to 7. In this case, this might be bromo. This might be best because it's 7.3, right? But because it was weak acid, we're gonna have to set up ice table.
That helps,
yeah,
thank
so
you.
yeah, that was a good question because you may have strong acid there, right?
Mm-hmm.
In other situations, so you have to identify that. Very good. Yeah. Any other question? Okay. I'm not going to erase it, just in case if you are writing something. All right. What about here? Titration of. You see this was base, right? This is base because you have molecule has ammonia somewhere, and if you draw restart structure, this will have lone pair electrons. This will be base. Most time you don't have to really worry about too much. If your molecule has nitrogen, is connected to hydrogen, it's probably weak base. Okay? Weak base with strong acid. Which of the following would be a good indicator? Okay. So do you see its similarity? Weak acid, weak base. Strong base, strong acid. It will be similar problem. So again, weak base with strong acid turn into this. And then they happen to be same concentration again. So you're gonna have to use the same volume. If you use the same volume, concentration becomes half. So the concentration of this guy after at aqueous point you have nothing left here. But this guy will be 0.050. So we have to come up concentration. So using that guy, now we start equilibrium and ice table. This is initial condition of ice table. At equilibrium, that will be this. So although the base and actually switches number-wise, it is still same, right? Number is still same. So again, x square over 0.050, to x. This time, it's k, or it's ka, because it's action. but it's conjugate action. Therefore, we need 10 to the negative 14 and Kb value. K value for that guy is, you have to look it up.
4.3 times 10 to the negative 10.
Say it again?
4.3 times 10 to the negative 10.
Okay, thank you. So that will give some number. This guy, we can approximate it to 2.250 x squared. So together, we can solve for x. X is inside the square root, 0.050 times 10 to the negative 14 over 4.3 minus 10. And we are calling x h plus, so that's h plus. So our pH will be just negative log of this number. And our pKa value should be similar to pH value. Okay. Indicate the pK value should be similar to pH at equivalence point. So which indicator do you choose then? C. Actually, I didn't. Inside of square root, 0.05. Divided by 4.3. A. So low, low, 2.97. What?
I might do that. Yeah, 2.97.
What do you have?
2.97.
Okay. So because 2.97, which one is better? D is better, right? Although it's different, this is still best among possible indicators. D is better. So that was all about the X base. Okay. The following portion, from now on, it will get a little easier than X base. So X base is the highlight of CHEM 2, and then supposed to be most challenging one in whole general chemistry. So you just went through that. Okay. From now on, it will get easier. But it's not too easy. It will be still challenging, but relatively easier. Okay. That's a good news, right? Yeah. All right. Solubility. When you have certain solid, like barium sulfate, and then put in the water, it dissolves. Simple example might be you put sugar. Sugar is solid in the water that dissolve. For sugar, it will be just aqueous phase, but it does not dissociate, right? Because this is a covalent compound, it doesn't dissociate. This is an ionic compound. So, solid form of barium sulfate will dissolve in the water and dissociate as ion, like this. Okay? So when we say soluble or insoluble, it includes both ionic compound and covalent compound. But covalent compound is boring in terms of solubility. We don't deal with this guy. You don't have to do much calculation. So we are focusing on this one. But that doesn't mean solubility is only for the ionic compound. It's for both. Okay? So when ionic compound dissolve, it dissociates as ion, and we can write equilibrium constant because anytime when you have equilibrium, so by equilibrium I mean is this reaction is not complete. Okay? For example, another example, a table salt. If you put table salt in the water, most time it completely dissociates. Right? But if you also put that like tons of table salt, at some point this may not dissolve anymore. That is what we call saturated solution, right? So even for this guy, at some point there will be equilibrium. Okay. So if you put any salt, there will be equilibrium. But if that dissolves very well, this is soluble salt. This is something we call insoluble because for this guy, you'll get lots of product because it's very soluble. For this guy, you'll have a little bit of product. So this is considered insoluble. Okay. And then, if you have double arrow, we can define K value because it means equilibrium. The product concentration over reactant concentration, but reactant is a solid phase, so you are not using this guy. And this is equilibrium constant. Now, equilibrium constant for acid, if you have acid in the reactant side, that is A, Ka. Equilibrium constant for, if you have base here, that will be Kb. If everything is written in terms of concentration, in general it will be Kc. If it's written in terms of pressure, it's Kp. This is more like a general term. This is more specific for acid. This is specific for base. In this case, you have a solid, right? So we say solubility product. This constant is called solubility product, Ks. And for the terminology, this equilibrium is between solid and solution, aqueous phase. Because it's not mixed uniformly, we call it heterogeneous equilibrium. That is different from when you have weak acid in the water, then it dissociates as ion. This is happening everywhere in the solution uniformly. This will be homogeneous equilibrium. This is heterogeneous equilibrium. Okay? Just for terminology. If you have calcium fluoride, because calcium is from the group 2, it will combine with 2 of halogen, in this case fluoride. Because of that, it is when it dissociates, calcium get 2 plus charge, fluoride is -1 charge, but you have 2 of them. So you get 2 and fluoride. And then for if you have constant expression, this number relates to power. So you have a scale here, while this one will be just first order. That means for silver carbonate, because it dissociates, give 2 of cation, which is the partial ion, and 1 anion. This number will relate to power in silver concentration right there. Okay? So you should be able to write a solid product for any compound. Right. You see there's some problem. So why don't you write solid product for this guy? Dissociation and KSP. So because you can write a KSP expression for any salt, let's see some the KSP value is listed in D12. If you go to D12, unit 1, there will be a table. Okay. Also, it will be available to you on one of these peer table. Okay. Don't worry about it. But you should be able to look for any KSP value. Because KSP itself is a product here. If the KSP value is big, so KSP value for these two compounds have just like that. Because this number is greater than that guy, this will be more soluble, relatively. It's very small, so it's considered insoluble, but this is even more insoluble.
So if what does the KSP value have to be for it to be soluble?
Let's say NaCl. Table salt is it's soluble, right? Everybody knows it's soluble. If I put 0.1 molar concentration of NaCl and it will dissociate, it will give you 0.1 mole of this, 0.1 mole of this.
Right.
If we multiply those two, your KSP, we don't define KSP for this guy, but 0.01, right? Which means there are two, it's considered soluble. So at what point it's considered insoluble? That was your question.
Yeah.
You will have to look it up. Maybe 10 to the -4. I'm not for sure, but maybe something like this. Or it's still considered soluble because that would mean 0.01 here, 0.01. Let's say you put like 1 mole concentration of solution. If that dissolve only 1%, it's considered insoluble. I would say this might be like an insoluble or soluble, you can debate.
Okay.
Because it depends on how much you put in here as well. If I put 1 mole of solution and you just only dissociate only 1%, it's kind of, insoluble. Okay. Solubility is something that actually relevant to your question actually. Solubility is something that, let's say I put NaCl in the water, how many mole will dissolve in the water, so you can say the concentration. Okay, if I put 1 mole in 1 liter of water, if everything dissolves, solubility will be 1. Why concentration is 1 mole? So in that case, solubility will be 1 mole, 1 molar concentration, because I put 1 mole of NaCl in 1 liter, everything dissolves, solubility will be just 1 molar concentration. Okay? So carbobromide solubility is this, which means if you put 1 mole into water, it's only like this much will dissolve, less than 1%. Okay? Calculate the KS value. Well, CuBr, let's use double arrow. Cu plus. Wait. CuBr. So then you shoot this plus. Not 2. Br minus. KST is copper plus Br minus. So if we know solubility is as that number, so let's call this solubility as S. If the acid amount dissolve, then here it will be S, there will be S, it will be S squared, which means 2.0 times squared. So So that make it 4 quantity minus 8. By the way, although constant has unit, if your constant do not have a unit, so do not write anything here. Silver sulfide has little that. Now silver sulfide will dissolve at 2H plus and S2 minus. So if S more concentration dissolve, then you have 2S here, 1S here, and the KSP is silver concentration raised to second power and the sulfide. So that means I have 2S square and S. So my KSP should be 4S square times S, which is 4S cube. Therefore, my KSP is 4 times solubility is what? That number 3.4 negative 17 and cube. You will have that number. Oh, that was the last slide.
Why is that 2S?
Because if you dissolve S amount by stoichiometric method, that will be twice of this. So if you dissolve S amount, you're going to put twice of it.